Hello, everyone. Welcome back to Math 162. So this is our fourth lecture in total, week 2, lecture 2. Again, I just like labeling my whiteboards like that just to keep it a little more clear and concise. And then when you're watching the YouTube replays, the title of the replay will always actually say the date. Why I choose to do it that way, I don't know. I could put the date here too, I guess. It doesn't really matter, though. I mean, I just figure when we're doing this live, you know the date, so I don't need to write the date. And if anyone really feels the need for me to write the date, just email me and I'll start doing it. But otherwise, I'm going to keep to my setup here. Not really a big deal, I hope. So as a reminder, we have completed 5.1 and 5.2. We completed those a week ago, so those are due today. Now, remember that all homeworks, all tests are always going to be due 11:59 p.m. unless for some reason I say otherwise, which I don't anticipate ever doing. So I'm not going to continue to put this reminder on the board every single day anymore. It should be an assumption. We will finish 5.3 and 5.4 today. 5.3, we were just at the cusp of finishing last time. So those are going to be due in a week on the 10th, again, by 11:59 p.m. Remember that our first test is going to just cover chapter 5. We're still not really ready to talk about that, but I would like to remind you that there will be a review available for you, and there will be at least 1 week warning before the test is given when I announce the test date and everything. So you will have a solid warning, and the review will be made available pretty early on before the test is available, and that you'll have 2 days for the test. But I don't want to waste any more time. I know I was a couple minutes late as always. Again, thank you for your patience. Like I said, I've got that class that ends right at 11 o'clock and my files have to convert. So it's just about impossible for me to be on time here. So thank you for your patience. I just want to remind you that frequently throughout the day's materials, I will be referencing what I like to call my little board cheat sheet. And this will change a little bit over time. In fact, you may or may not have seen this unit circle up here before. Maybe you have, maybe you haven't, depending on when you've watched it, but that was added at some point. And I just like to have this up here so I don't have to constantly draw the 45-45, 90 triangle, the 30-60, 90 triangle, the reciprocal relationships, the Pythagorean relationships, the smart trig class relationships. These are things that we'll say over and over. I'll quickly flip to them. Sometimes I will write them again during a problem. It just depends on the scenario. But these are things that you should continue to replicate until you have them all memorized, unless you're going with a completely different route. Like I said, as long as you can get a problem done, whether through great methods of A to B to C to D or just pure memorization, it's up to you. I do prefer the logic and reasoning side of things because as pre-calc students, we really have to understand the mechanics of everything, and just straight up memorization can only get us so far ultimately, but it's your life, it's your choice. Again, as long as you can get good answers, that's fine. But not understanding the actual mechanics could end up hurting you when you get to calculus and beyond, depending on how far you're going in the calculus sequence. Are you engineer tech where you stop after 1 or 2 calculuses? Or are you going to go into true engineering? That's a terrible way to say that. It's just without the tech attached to it, where you actually go through Calc 3, or are you going computer science? Maybe you're going to be math, whatever. There's a lot of different roads for each student. So again, you'll see this referenced, but we're going to pick back up in 5.3 where we left off, doing problems like cosine of 330 degrees or sine of 150 degrees, where we need to use reference angles. So we take our actual angle and find out what that angle would be if it had been in quadrant 1, doing the sine or cosine or tangent or whatever based on these 2 triangles, or if you prefer pure memorization. But then remembering that because we're in a different quadrant, it's possible that it could be a positive or it could have been a negative based on the x and y coordinates, which relate to sines or cosines. If you're talking about a tangent, that's the ratio of the 2, so it still has a relationship there. And we said if you don't like the x, y, and ratio and plus and minus pattern memorized that you can see in the picture with the blues and the reds, then you can just memorize a smart trig class, and boom, that'll get you all your pluses and minuses that way. All right. So again, let's pick up where we left off, and we'll be getting into C. We did A and B last time. If you need to see them again, please check last week's lecture. I'm sorry, last class's lecture. I said the wrong word there. Oops, wrong color. C.
Next, let's do the cosine of 330 degrees. So let's find our reference angle first, so we can go to the side and drop our quadrants. And if you don't have to do this drawing, then you don't have to. Like I said, some of you will just play with let's add or subtract 180. Nah, those numbers are going to be too big or negative. Let's try 360. Well, if you did 360 minus 330, you'd get 30. There you go. There's your reference angle. And you could say, oh, I know 330 is in quadrant 4. But again, some of you will need to draw this up. This would be 330 degrees, roughly. That's our actual angle, which makes this tiny little chunk our reference angle. And that would be found, the only way to get an answer between 0 and 90 is to do 360 minus 330, the original angle, which would be 30 degrees. That is our reference angle. So that says the cosine, the cosine of 330 degrees should be the exact same thing as the cosine of 30 degrees, but maybe positive, maybe negative. We're going to have to figure that out next. All right, so since we're in quadrant 4, wrong color. Since the original angle is in quadrant 4, that says the cosine is, let's see, cosine is the x value. Quadrant 4 means we're going right, so it's positive. Or a smart trig class, so the fourth one is quadrant 4, ASTC, that says cosine's positive in quadrant 4. I don't care which method you're using. If you have some third method that works for you, that always works, use that. So cosine of 330 degrees should be equal to the positive version of cosine of 30 degrees. How do we find the cosine of 30 degrees? We go back to those two triangles. One of them is 45, 45, so that's not it. We need the 30, 60, 90. So we go to the 30, 60, 90 triangle over here. So this is our angle this time, which makes the 1 the opposite, the square root of 3 the adjacent, and the 2 the hypotenuse. Cosine is COA, C-A-H. Well, I don't know why I said COA. Please pardon me there. I was looking at the TOA part. C-H-Ca, C-A-H, adjacent over hypotenuse. So it's going to be the square root of 3 over the 2. Square root of 3 over 2. So it's the positive square root of 3 over 2. But I'm not going to write the positive sign anymore. Please don't write positive signs in your answers in my math lab. It'll probably mark it wrong. And nobody wants that. Nobody wants to have a right answer and it's wrong because you wrote a plus sign. That's just silly, right? All right, last one of these, and let's mix it up. The cosecant of 240 degrees. Actually, before that, I want to point out, look at the answers to A and C. The sine of 120 is the same as the cosine of 330, square root of 3 over 2, square root of 3 over 2. There are tons of trig functions that have the same outputs because they're the same as the sine of 60 degrees or the cosine of 30 degrees. So the cosine of 30 is the same as the sine of 60, is the same as the cosine of 330, is the same as the sine of 120. That is why I cannot stand blatant memorization of the unit circle. There's too many overlapping answers. There's too much room to make a simple error in a plus or a minus or a square root somewhere. All right, so 240, where's that put us? Well, 180 is the quadrant breaker for 2 to 3, so this must be in quadrant 3. So our angle has to be down here somewhere. So here's the true angle theta, and that's the 240 degrees. But we need our reference angle to be this little slice right here, not the bottom one. That would swing to the y-axis. So there's our reference angle. And 240 degrees, we got to play with 180 to get an answer. If we do 180 minus 240, it'll be negative. So we go 240 minus 180, which will give us 60 degrees. That's our reference angle. So the cosecant of 240 degrees will be the same thing as the cosecant of 60 degrees, with the exception of maybe it's positive, maybe it's negative. Well, since our angle is in quadrant 3, cosecant is it positive or negative? Well, you might say, well, a smart trig class has nothing to do with cosecant, and I'd say it does implicitly, because cosecant and sine are reciprocals of each other. Sin, sine. Cosecant and sin are reciprocals of each other. So if sine's positive, cosecant's positive. If sine's negative, cosecant's negative. So we're going to use a smart trig class based on sine. In quadrant 3, sine is negative, and that's because we're going down. If the sine's negative, the cosecant's negative. So cosecant is negative. So we're going to choose the minus for this one. So the cosecant of 240 degrees would be the negative cosecant of 60 degrees. Now, some of you may go ahead and switch this to being 1 over sine of 60 degrees, and that's fine. But let's actually try and remember the relationship between cosecant and its opposites, adjacents, and hypotenuses. So as a reminder, cosecant, if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. So we got to go to the 60-degree reference triangle. So we're up here this time, and cosecant is going to be hypotenuse over opposite. So hypotenuse over opposite. That'll be 2 over square root of 3. So this will be negative. I'll stop changing the color after a second. Negative 2, again, that was the hypotenuse over the square root of 3, which was the opposite. The 1 was the adjacent in reference to 60 degrees. But this is not okay because we have a square root in the bottom. I'm going to switch to an orange. So we multiply top and bottom by square root of 3, giving us for a final answer, negative 2 square root of 3, not final, one more step, over the square root of 9, which is negative 2 square root of 3 over 3. That's our answer. If you miss that negative sign, this is completely wrong. And the funny thing is, I don't even know that it warrants partial credit because so many students, I know they're just missing half of the entire problem. Yeah, you understood the relationship between opposites and hypotenuses and adjacents, but you completely disregarded a smart trig class, the fact that you're positive or negative for different trig functions in different quadrants. So I know a lot of students want to be really upset with me if they wrote this as a positive, my math lab marks it completely wrong on a test, and then I don't give any partial credit. I really, really, really don't think you deserve a lot of partial credit for that. Maybe a point. Because all of those concepts are tied together.
Don't worry, that frozen screen was intentional. I had to switch videos. All right, so that was it for that little section, and I'm just going to give a quick reminder about what we did for ABCD, the processing, and then we're going to move forward to a couple of word problems that I meant to do from, I think, 5.2, and then we'll pick up 5.4. Just letting you know what that little crazy weird thing that happened right there was. Sorry about that.
I'm sorry if you're having issues at the moment, though. All right, so we figure out our quadrant. We figure out the trig function's sign, whether it's positive or negative in that quadrant. And then we just do the trig function of the reference angle, which will generally fall onto one of those two triangles, the 30, 60, 90, or the 45, 45, 90. So again, we did 4 of those examples. These are really good examples, one of my favorite types of problems. You will definitely see these in homework. You will definitely see this on your first test, on the final. It will persist. All right, so with this idea, let's try and work backwards. And it's always the working backwards that can be a challenge, but we have to. We already did all this stuff. These are old notes. I can delete that. So, example 5. Given that the cosine of an angle is equal to 1/2, and the angle is between 0 degrees or 0 radians, we're using radians actually, and 2 pi. Less than, not less than or equal, less than 2 pi. The 0 gets the or equal, the 2 pi does not. This is pretty common. We're going to find all angles. Triple underlining this. You know how I like to point out what students tend to do wrong on tests and things? This is one of those situations. Spoilers, there's more than one answer. Spoilers to what students tend to do on tests, they only give one answer. That means they get it wrong. This is a type of problem that quite often has 2 solutions. They can have one occasionally. There's certain conditions that they only have one, but it's usually 2. So last time what I was doing was I'd say, what's the cosine of 330 degrees? And then we would find the ratio of opposites, adjacent, tangent, whichever the 2 of the 3 we're supposed to be using, and we're writing out a ratio. We had the angle, and we were trying to find the ratio of those 2 to 3 sides. This is a very different problem. I did not give you the angle this time. I gave you the ratio of opposite, adjacent, hypotenuse, whatever it is, relative to the trig function. And I said that your angle is somewhere in those first 360 degrees, between 0 and 360, including 0 but excluding 360, because they're the same degree, so you don't want repeats. And to find all solutions. So that is supposed to be the hint that there's more than one solution. I could also say find any angle that would solve it, and that may be like less of a hint, but it's still a hint. So what's going on? Why are there 2 solutions to this? How do we find them both? So we're trying to find any angle that, so for a cosine SOHCAHTOA, that's adjacent over hypotenuse, we are trying to find an angle such that when you take the cosine of it, its adjacent is 1 and its hypotenuse is 2. So we're trying to basically make a reference triangle with an adjacent of 1, hypotenuse of 2, which means we're going to end up at the 30, 60, 90 triangle. But we're supposed to be going full circle. We're supposed to be looking at all 4 quadrants, not just quadrant 1, and quadrant 1 may not even be the actual answer. So you have to think about, okay, well, in what 2 quadrants is cosine? This is positive. If it was negative, you'd say, what 2 quadrants is cosine negative in? And then you'd end up having to take your reference angle and putting it in those quadrants. So that's why this is a little different and why people tend to ignore the second answer. And unfortunately, that's a giant issue. Okay. So because this is cosine of theta equals 1/2, let's do the cosine of theta prime equals 1/2. Now, if there was a negative here, I wouldn't write the negative here. So we drop the signs and we switch to a reference angle. So we dropped the plus or minus sign and we switched to a reference angle. Reference angle. Because cosine of an angle has the same cosine of a reference angle, or for any trig function really, with maybe just a plus or minus difference. So if the cosine of the angle is 1/2, that means the cosine of theta prime is also 1/2. If the cosine was negative 1/2, that means the cosine of theta prime would have to be positive 1/2. Reference angles, all positives, no negatives. So when you have this set up, that means if you draw a right triangle out of this, here's your right triangle. If this is the angle we're going for, our reference angle, because it's cosine is adjacent over hypotenuse, the adjacent would have to be 1, the hypotenuse would have to be 2, and then by memory we would know this has to be square root of 3. If you are not memorizing that, you can find it based on Pythagorean, but it's going to take you more time than it should. This means theta prime is equal to, well, which one was opposite the square root of 3 in this? Was it the 30 degrees or was it the 60 degrees? Well, here's the 30-60 triangle. The square root of 3 is opposite the 60 degrees. But this problem, well, I'm not going to focus on this aspect actually. So that means it's 60 degrees or pi over 3 in radians. So the parentheses is just the same thing. I'm not saying it's 60 degrees times pi over 3. I'm saying it's 60 degrees in one version, pi over 3 in another version. Just annotation. So because this is the triangle we drew up, because we knew the cosine is adjacent over hypotenuse, we knew this had to be 1, we knew this had to be 2, which makes this square root of 3, and the angle opposite of a square root of 3 is always 60 degrees. So that's our reference angle. But we need to put this quadrant. Well, which quadrants is cosine positive? In quadrants, where cosine is positive. So a smart trig class, you could work it out that way. You could remember that cosine goes like the x value, the x coordinate. So x is positive when you go right, which means quadrants 1 and 4. Or you've memorized and drawn all this up right after starting your test, whatever, and you can see that cosine is positive in quadrant 1 and in quadrant 4. Again, all based on a smart trig class. A smart trig class gives you all the blue ink. The red ink is just the ones you don't get. So cosine is positive in quadrants 1 and 4. So we need angles in quadrant 1 and 4. Our reference angle of 60 degrees is actually in quadrant 1. So theta prime equals 60 degrees is in quadrant 1. So it is one of the answers. So we can say, I'll use subnotation for this. The first angle is 60 degrees. That's the first possible answer. And if you go back to the original black ink, the original problem, the cosine of 60 degrees is positive 1/2. But we also know that the cosine of the angle in quadrant 4 that would have 60 degrees as its reference angle would also give us positive 1/2. So we need to put this 60 degrees in quadrant 4. To find the second answer. So we can draw up our quadrants. Now our 60 degrees is a reference angle. Remember, we swing from the x-axis. So this has to be our 60 degrees. So that was our reference angle, theta prime, which means the real angle would be this. This is the actual angle that would put us in quadrant 4. So you've got to do that kind of same implicit math. Do you think you should be messing with 180 or 360, order of subtraction? Remember, you're just trying to get an answer that makes sense. That's the point. So if you do 180, there's no way you're going to get an answer in quadrant 4. So it's 360. So if you try doing 360 degrees minus 60 degrees, you would get 300 degrees. If that answer makes sense, it's right. 300 degrees is in quadrant 3. That's between 270 and 360. So that would be the second angle. So your solutions, the first one's 60 degrees. The second one is 300 degrees. You might be just separating these by commas. If it tells you to put them in radians, this would be pi over 3 and 5 pi over 3. If you did 2 pi minus pi over 3, or if you just convert 300 to radians by multiplying by pi over 180. Remember, those conversions are never actual problems. It's just something that you need to be able to do on the fly. So I have the answer in degrees, I have the answer in radians. My math lab might specify which one it wants. It might not. Pay attention to the instructions. If my math lab asks for, if it's a test question and they ask for the answer in radians and they give degrees, I don't have to give partial credit. It depends on the context of the problem. Most of the time I would give 4 out of 5 points for that, but there are some instances, and I'll tell you when, that you actually have to answer in radians. You are not supposed to answer in degrees. There's some applications, kind of some inverse trig functions that you have to answer in radians. All right, so that was example 5A. I forgot to write my A. We're going to do a B and a C. Again, this is probably the problem, the type of problem that kicks a lot of students in the pants because they think it's one answer and it's two. And they always do reference angles as their answer. And sometimes they'll get that wrong because maybe it was supposed to be in quadrants 2 and 3, and then the reference angle is no longer accurate anymore. You were supposed to have put that in 2. So you get none of them correct. All right. B. Given that the tangent of our regular angle is -1, and our angle has to be between 0 and 2 pi, find all angles. Pay attention to these restrictions. Sometimes you'll get a curveball thrown at you and the restrictions are from 0 to pi, or maybe from pi over 2 to 3 pi over 2. And when you have that, that means they're eliminating quadrants and maybe you only actually have one answer in that case. There could still be 2, but maybe there's only 1. So you have to pay attention to every little finer detail. But both of these are still looking full circle. Maybe I'm spoiling something in C. Hint, wink, nudge. All right, so same idea. We need to set up the reference angle problem, which means we'll ignore the negative sign. So we're going to say, try and use the same language. Let's do the tangent of theta prime equal to 1. So I've just dropped the negative sign. If the tangent of the angle is -1, that means the tangent of the reference angle has to be +1 because there's no negatives with reference angles. Now tangent, that's TOA, T-O-A, it's opposite over adjacent. Now this 1, you might actually want to write out as 1 over 1. It's usually a good idea to write out those right-hand sides of trig functions as a ratio because all trig functions are ratios of 2 sides of a right triangle. This tangent is the opposite over the adjacent. So now we can tell that this 1 is the opposite and this 1 is the adjacent. So that means we're drawing up the reference triangle with theta prime here. The opposite's 1, the adjacent's 1. Well, that's the 1, 1 square root of 2 triangle that you're supposed to memorize. Or be able to Pythagorean it up and remember that, all right, well, if these sides are the same, that says theta prime has to be 45 degrees. Again, here was it actually drawn up originally. If the sides are 1, 1 square root of 2, the angles have to be 45 degrees. Also known as pi over 4. So our reference angle is pi over 4. Our reference angle is pi over 4. But the reference angle may or may not be one of the answers. So we got to think, okay, where is tangent negative? So last time it was cosine and it was positive. And we said cosine was positive in quadrants 1 and 4 based on the smart trig class. Now we need the tangent to be negative. Well, based on a smart trig class or based on the x and y coordinates and all that jazz, tangent's negative in quadrant 2 and in quadrant 4, because the ratio of y over x is negative, which just means one of them is negative. If the tangent had been a positive one, we'd pick quadrant 1 and 3, but we're picking quadrant 2 and 4 because it was negative. So tangent of an angle is negative. Let me use the same way I wrote it out. Tangent of the angle is negative in quadrants 2 and 4. So last time the reference angle was one of the answers. That's not the case. Our answers are actually in quadrant 2 and 4, so we have to make sure we put our reference angle once in quadrant 2, then once in quadrant 4. So please note, theta prime is not an actual answer. We got to put it in quadrant 2 and 4. So for the first one, let's put an angle in quadrant 2. Here's quadrant 2. Now the reference angle is the 45 degrees, which is right here from the x-axis. That's our theta prime, which says that the actual angle is this. Now that's a quadrant 2 angle, so the answer should be somewhere between 90 and 180 degrees with a theta prime of 45 degrees. If you play around with 180 and 45, you can see that the first solution should end up being 180 degrees minus 45 degrees. Sorry, I got distracted, which is 135 degrees. So that's our first angle. The second angle, we need to draw up in quadrant 4. So our reference angle would be this one. That's the 45 degrees this time, which means our actual angle is all the way around. Big angle, between 270 and 360. So to play around with 45 degrees to get an answer in the appropriate size, you would have to do 360 degrees minus 45 degrees, which ends up being 315 degrees. So our solution in degrees is 135 and 315. In radians, what's that? 3 pi over 4 and 7 pi over 4. I will leave the actual conversions there up to you to try out. I do encourage you to practice those conversions as much as possible. Multiplying by pi over 180. Or you could have done 2 pi minus pi over 4, which is 8 pi over 8 minus pi over 4. 8 minus 1 is 7 pi over 4. That would be the second one. The first one, you would have been doing pi minus pi over 4, which is 4 pi over 4 minus pi over 4, which is 3 pi over 4. C, one more. Enough room? Yes, enough room. So given that the cosine of the angle is equal to the negative square root of 2 over 2, and your angle is between pi and 2 pi, no or equals, bad habit of mine. Find all angles. So this one is unique for 2 reasons. First reason I already alluded to earlier, this is not in all 4 quadrants. This is just quadrant 3 and 4. So cosine is negative in 2 quadrants, which would make you think there would be 2 answers, but it's only negative in one of these 2 quadrants, which means we're only going to actually have 1 answer. So even though cosine is negative in 2 of the 4 quadrants, because we're limited half of them, cosine is only negative one of them, just 1 answer. So There are cases with only one answer. I alluded to that earlier. And when we open ourselves up to what we call the quadrantal angles, which is coming today, which are the 0, 90, 180, 270, and 360, once we learn how to do sines, cosines, and tangents of them, we can actually use the full 360 degrees and still sometimes only have one answer with those because they work different than the 30, 60, 90, 45, 45, 90 triangles. All right, so before we actually get into what the answer is, we need to go to the reference angle. So let's try the cosine of theta prime equal to, ignore any positives or negatives, square root of 2 over 2. Now, for asterisk memo, this is going to be an issue more than once in this course. If you draw up your right triangle with an adjacent of square root of 2 and a hypotenuse of 2, I'm going to do this not in a good way for a second. So if you did it this way, if you said, here's your reference angle, the adjacent square root of 2, and your hypotenuse is 2, it turns out that this side is also square root of 2, but when you look at this and you try to go to what I've told you to memorize, it's not either of these things. And that's because it is actually this one, but instead of ones on these sides, it's a different base value. So everything's been multiplied by said base value. So this is kind of ugly, and that's why I don't really suggest doing it. Now, you can eventually figure out, oh, well, these are the same, so it's 45 degrees, but the issue doesn't fix itself so neatly with the 30, 60, 90 triangle. So we, at this point, should have done the rationalizing of denominators many, 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 many times by now. So if you had something, I don't want to start with red, I want to start with black. 1 over square root of 2. When you rationalize this, you multiply top and bottom by square root of 2, and you end up getting square root of 2 over the square root of 4, which is the square root of 2 over 2. The point being, this thing is the same thing as this thing. Now, drawing up that right triangle with the square root of 2 over 2 version sucks, especially when it's a 30, 60, 90 triangle configuration. So it's more about understanding, all right, when you see the same number top and bottom with a square root in the top, this has been rationalized in the bottom, and this would have been the original figure. It's something that you'll see over and over and over, so we expect you to kind of memorize it, I guess, or be able to do the thing I already showed you. I said, isn't great, but works. So instead of doing this, please note that it's the same as saying the cosine of theta prime is 1 over the square root of 2. Because that way, when you draw up your reference triangle, so theta prime, you have your adjacent of 1, your hypotenuse of square root of 2. I know this is going to be 1, and I know that that reference angle is 45 degrees because we can see it on our cheat sheet on our board. Again, the cheat sheet that you would write when you start the test, not before. 1 square root of 2. It just makes it easier to configure that. And again, that same issue can pop up with the 30, 60, 90. So we know our reference angle is 45 degrees, but we need to put this in which quadrant? Well, we're limited to quadrants 3 and 4. So we're dealing with cosine. Cosine is negative. In quadrants, cosine goes like x. X is negative when you go left. Left means quadrants 2 and 3. If you didn't like that rationalization, you go back to a smart trig class. Cosine ends up being negative in quadrants 2 and 3. Again, a smart trig class actually gives you the blue ink. The red ink is just whichever ones you don't fill out. All smart sine, trig tan, class cosine. Then the rest are negatives. So, because cosine is negative in quadrant 2 and 3, but we're only looking at quadrant 3 and 4, we're going to put it in quadrant 3 only. Because quadrant 2 is not part of the solution range. So we're going to put 45 degrees in quadrant 3. Here's an angle in quadrant 3. We would swing this way for our theta prime. That's our 45 degrees. which means the actual angle is doing this. That's our actual angle. And playing around with 180 and 45, you could eventually figure out that you would need to add them. If you subtract them, you're going to get answers in either quadrant 2 or a negative answer. So it's that you need to add them. Actual solution, and no 1 or 2 because it's the only one, will be 180 degrees plus 45 degrees, which is 225 degrees. Or in radians, that would be 5 pi over 4. Today is the 14th. So that means we just finished 7. Sorry, my notes still say 7, 5.3. So 5.3 homework we do, and today's the 14th to the 21st. So make sure that you work on those. 5.1 and 2 have already been due because we had that Monday off last week and it took us 2 classes to knock out final numbers and periodic functions. It's in the center. It's a little bigger. Spacing, enter 10,000 times. So we're going to introduce something known as the unit circle. Now, this is not going to be me writing 6 different answers for a whole bunch of different degrees, 30, 60, 90, 45, 120, 330. That's not what I'm going to do with the unit circle. You will never see me draw the unit circle up, never in my life. I'm going to introduce what the concept of a unit circle is. This is a circle, a radius, 1 unit, 1 inch, 1 meter, 1 mile, whatever the units you choose to be in, 1 unit. So it's a circle with a radius of 1. Now, before, we said, cool, thank you for letting me know. So before we said that, and I got to write these up, the cosine of x went like the x value over the radius. The sine, why did I say cosine of x? Cosine of theta. Cosine of theta. Cosine of an angle goes like x over r. Sine of an angle goes like y over r. And the tangent of an angle goes like y over x. And we built the smart trig class based off of that. We did all the plus or minus signs based off of that, based on the coordinates. Well, with a unit circle, the radius is 1. R is 1, and we don't need to write it. So this is where we get that final version, which I've already been kind of using, but cosine really just goes like the x coordinate. Sine really just goes like the y coordinate. Tangent really just goes like the ratio of the two. That one doesn't get simplified, unfortunately, but it's fine. It just means that the size of your circle is irrelevant, but we like a unit circle because it's a radius of 1, which makes things easier. So I'm going to draw this up. The best circle I can do. There we go. And this would go through our quadrants. I wanted to draw them around that. So x, y. So standard point system. So let's say I have this point right here. This is our point, and that point is x comma y. It's not p times x comma y. It's saying that's a point, and its coordinate is x comma y. Wherever this point is on this unit circle, because it has a radius of 1, so this distance right here is a 1, so it's out 1 all around it. So that point would help us do all those trig functions. So if this was the 0.3, comma 12, if that actually worked, which it doesn't, let's say 0.3, comma, I don't know. I can't make up those numbers off the top of my head and actually make them accurate. So let's just say A and B. So if this point was A, comma B, you can do all that switching quadrants to reference angles and stuff like that. But you can just say that those two values would give you all the trig functions. If you want to know the cosine, it's just the x value if you're on the unit circle. If you want to know the sine, it's just the y value if you're on the unit circle. The cosines, the x sines, y, tangents, that ratio. And then you have those three reciprocal functions. Secant would be 1 over x, cosecant would be 1 over sine, and cotangent would be x over y. But I choose not to write all the reciprocal ones down generally because you can do exactly as I just said. So also that point, in case it's not clear, that has a radius of 1. So for example, blue, black, example 1, we're going to just find all 6 trig functions. For a point on the unit circle that's negative 1/2 and negative square root of 3 over 2. Now, I don't actually have to say that it's on the unit circle. If you tried to determine the radius of this, it would turn out to be 1. If you took the square root and squared both of those and added them, you would get 1. So it's on the unit circle whether I told you that or not. So if you wanted to draw up that unit circle, we'll do it much smaller this time. Now both of those points are negative, so that means we're going left and up. So here's our unit circle. X, Y. I'll draw one little radius demonstrating that that is a distance of 1. But the point that we're actually on is at negative 1/2, comma negative square root of 3 over 2. So we're going left. So this right over here would be a negative 1. This right here would be negative 1. So we're going to go left halfway, and then up, and then down. If I said up earlier, I meant to say down. Down, square root of 3 over 2. Now I don't know exactly where that is, but trust me, it's going to be right here. I don't figure that out based on numbering. I figure that out because I go down until I hit the circle. The point's on the unit circle, it better be going down that far. So that was me going left halfway and then down till I hit the circle. So this is our actual angle. The red is the angle. The blue was just me demonstrating the radius is 1. So here is our angle. Now, I do a theta here, but and I'm going to erase it, because when you go to this unit circle, very often they'll do that the angle is t. So this is me saying that the angle is t. It's not something I'm going to do in class traditionally. I'm not a fan of using the letter t for obvious reasons. They can look like plus signs. I don't have the best handwriting. There's lots of problems with it. So I'm going to stick to theta for the most part. But for various functional reasons, they start using x's and y's and t's instead of just a theta. And I don't really like using x's and y's because the x's and y's are already associated with coordinates. So that's probably a bad idea. I've seen people do it, but it's a bad idea. So we're trying to find the sine of t, the cosine of t, the tangent of t, et cetera, et cetera, et cetera. Well, because we're on a unit circle, the trig functions are just the coordinates or the ratio of the coordinates. The cosine is literally the x coordinate. The sine is literally the y coordinate. And if you don't trust this, you can draw up a whole bunch of different right triangles, and it will turn out that since the radius is 1, your hypotenuse is 1. So when you go x over r, or opposite over hypotenuse, however it is you're doing it, the denominator is going to be 1 and it's unnecessary, and you just get the x coordinate. So the sign of this would be the y value. So negative square root of 3 over 2. The cosine of this would be the x value. So again, sine is the y value, cosine is the x value. Only when you're on the unit circle. If you're not on the unit circle, you've got to do the opposite divided by the hypotenuse, or y divided by r, whichever one you're doing. So the cosine is the x value, well, that's negative 1/2. Tangent is the ratio of cosine to sine, or the ratio of y to x. Negative square root of 3 over 2. Then on top of the negative 1/2. This one will actually have some work to do, though. A fraction divided by a fraction, you're going to see it all semester long. We've already seen it. You've got to remember that this is negative square root of 3 over 2 division symbol, negative 1 over 2, which is the same thing as negative square root of 3 over 2 times negative 2 over 1. The negatives will cancel. The 2's will cancel, telling us that the tangent of our angle, again, the 2's cancel, the negatives cancel, it's just square root of 3. For the other ones, for the reciprocal functions, let's do cosecant of t. Well, that just flips the sign. Sine and cosecant are flips of each other, so that's negative 2 over square root of 3. But you're going to have to rationalize that. You're going to have to multiply top and bottom by square root of 3 over 3. Square root of 3 over square root of 3. That is 3 times 3 is 9, square root of 9 is 3. I'm not going to show that middle step anymore in this course, probably. So our cosecant is negative 2 square root of 3 over 3. Our secant of theta or t, whichever you prefer, just flip the cosine. Secant and cosine are flips of each other. So that's negative 2 over 1, which is just negative 2. Our cotangent of the variable, the angle, that's just flipping the tangent. Now that tangent was square root of 3 over 1. You don't write the over 1 part traditionally, but flipping that gives us 1 over square root of 3, which we have to rationalize the bottom. So square root of 3, that was an ugly 3. Looked like a B. And that'll give us square root of 3 over 3. If you don't remember this idea, it's going to be a much worse problem. This is what it would look like alternatively. If you said, all right, we have this point here. Again, that's where our angle was. Sorry, angle's here, negative, negative. Draw it up. If you do that, there's our angle theta, where then you want to make a reference angle out of it, which puts your reference angle there. Well, you have to use the coordinates to figure out how far left and how far down to go. So zooming in on that triangle, because the x coordinate's negative 1/2, that says we're going left 1/2. Because the y coordinate's negative square root of 3 over 2, that says we're going down square root of 3 over 2. But when you draw up triangles like this, you're technically not supposed to put the negatives. And like I said, some people do, and some people don't. But technically, they're not supposed to be there. Geometry does not have negatives in this fashion. And then you could say that this side, you can figure it out by a Pythagorean. If you call that c, then c is equal to the square root of 1/2 all squared plus the square root of 3 over 2 all squared. 1/2 squared is a 1/4. Square root of 3 squared is 3. 2 squared is 4. 1 plus 3 is 4. Square root of 4 over 4 is the square root of 1, which is 1. Oh, wow, it was a unit circle. It was a radius of 1. So now that you have that c is 1, you could do your opposite over hypotenuse. You could do your adjacent over hypotenuse, and you would get the exact same answers except for all the minuses that are needed because the minuses are there because you're in a specific quadrant. So you'd have to remember, oh, I'm in this quadrant, so the sine is negative, and the cosine's negative, and the tangent's positive. You would still have to pair that with a smart trig class. Whereas if you happen to know a point is on the unit circle, which is pretty rare, but if you do, then you can just completely rip off the x and y coordinates, the ratios, x coordinate, y coordinate, ratio, flip, flip, flip. I've said this a few times, but trigonometry does not have a lot of original ideas. We are really just kind of spinning around the same circle, pun intended, over and over and over. But at first we kind of open up to other options. We go from just part of the circle to all of the circle. Then we go from, all right, well, let's just make from the circle being any size to a radius of 1, so we can simplify some rules. Then eventually we do something else, and then eventually we do something else. But there's not a lot of concepts. So this idea of using the unit circle to find the trig functions, honestly, we don't really use it for problems like this. This is not a typical problem. So when do we use it? We typically use this for what we call quadrantal angles. Where 0, 90, 180, 270, 360 degrees, and 540, etc. Just keep adding 90. Or in radians, 0, pi over 2, pi, 3 pi over 2, 2 pi, etc., etc., etc. So it's a cool idea, it works, but honestly, there's just not a lot of times where I happen to give you a point that's on the unit circle. If I'm giving you a point, it's probably not on the unit circle, and you have to fall back on this idea anyways, getting the hypotenuse, paying attention to the quadrants, all that stuff. It's still good to know that sine goes like y, cosine goes like x, because that's a great way to do the plus or minus patterns. It's also a great way just to kind of further understand things, especially if you ever have to do anything with polar coordinates. So how is this helpful for quadrantal angles? Because they're going to come up quite a bit. And the transparency is just a little more there. The point numbers aren't so weird. It's just ones and zeros and negative ones and zeros. So big picture. So here is our unit circle. I forgot that I can't just erase part of something, so I got to start over. Little better. Not a perfect circle, but good enough. So we're going to assume this radius is 1 again. That's not me pointing out any particular angle. We're going to specifically talk about 0 degrees, aka 0 radians. We're going to talk about 90 degrees, which would be pi over 2. We're going to talk about, sorry, this circle got just a little ugly there. We're going to talk about 180 degrees, which is pi. We're going to talk about 270 degrees. That looks like a 2, doesn't it? 270 degrees, which would be 3 pi over 2. And then also 0 degrees is also 360 degrees, or 2 pi. So those are the 4 angles we're going to stick to for the idea of the unit circle. Now again, can you use the unit circle in other ways for other angles? Yes. Is it my preference? No. You do whatever you need to do to get things right, though. I don't teach you to just use a method I've taught you. I teach you methods, multiple methods when I can, but if you have something that always works 100% of the time, do it. But what you might find out is you think you have something that works and then it fails sometimes. All right, so these as coordinates. Let's list these points as coordinate pairs. So this point right here is going to be the point, so we're going right 1 and up or down nothing. How do I know I'm going right 1? Because we're on a unit circle. This distance going to any point has to be a distance of 1, and if I'm not moving up or down, it has to be 1, 0. Right 1, up nothing. This point up here this coordinate would be, we're not going left or right at all, so the first coordinate's 0, and then we go up 1, so a 1. You've got to remember how your coordinates work. If you don't, go spend hours practicing it. X comma y, right comma left, or I'm sorry, right comma up, or left comma up, or left comma down, whatever. This point over here, we're going just entirely left. Going left means -1, comma 0, left 1, up or down nothing. Then going straight down to 270 degrees. We're not going left or right, so that's a 0, comma. We're going to a point that's 1 away from it, but it's down 1, so 0, comma -1. This is going to be the next thing that I add to my cheat sheet over here. I'll start doing this. A little prettier though. I'll start drawing a quick little circle with points on it. 1, comma 0, 0, comma 1, point, sorry for that, -1, comma 0, and 0, comma -1. This is the next thing that we'll reference over and over and over and over and over. These are our quadrantal angles, because the sine, and we'll use that, and we'll use these two things paired together. So what's the sine of 0 degrees? Whatever its y coordinate is. What's the cosine of 180 degrees? Whatever its x coordinate is. What's the tangent of 270 degrees? The ratio of the y and the x coordinates. I think it's much more important to understand how to develop these things than just blatant memorization that the sine of 0 degrees is 0, the cosine of 0 degrees is 1, the sine of 90 degrees is blah, the cosine of this is blah. Understanding the logic and reasoning helps you understand why it is. Blatant memorization, a month from now, you're going to forget it. But if you understand the logic and reasoning, it tends to stick with you a lot longer. At least it works that way for me. All right, so using just this, let us develop 12 different ones. So again, just sines, cosines, and tangents. The reciprocal ones, just flip them and you get the answers. I'm going to pull out just a little in terms of zoom. So the sine of 0 degrees. So then the cosine of 0 degrees and the tangent of 0 degrees. Let's knock out this one first. Let's do one angle at a time. So we're only looking here. Sine, now remember that sine will be the y coordinate. Cosine will be the x coordinate. Tangent will be the ratio of the two of them. So sine of 0 degrees is the y value. It's 0. Cosine of 0 degrees is the x value, which is 1. Tangent is the ratio of y over x. Well, that's 0 over 1. 0 divided by 1 is 0. There we go. Easy. Again, this is all because sine is really y over r, but the r is 1. It's no reason to write over 1 every single time. This is the strength of your quadrantal angles and the unit circle combined together. All right, so if you wanted to know, I'm going to erase this one in just a second, but if you wanted to know the cosecant of 0 degrees, you just flip the answer to sine. So sine was 0 over 1, so cosecant should be 1 over 0. Now, spoilers, anything divided by 0 is undefined. Yes, there are trig functions that do not have answers of particular angles. So I'm going to erase that. I'm only going to show the work for sine, cosine, and tangent, but that's how you would go about doing. If you wanted a secant, just flip cosine. Cosine's 1 over 1. Flipping that gives you, coincidentally, 1 over 1. They can have the same answer sometimes. There we go. So next up we'll focus on the 90 degrees. So we're up on that point 0, 1. So the sine of 90 degrees, sine takes on the y coordinate. The y coordinate is 1, so the sine is 1. So here's a fun fact. Cosine starts at 0, works its way up to 1 slowly in a nonlinear fashion, which we will start talking about in the next section, how this actually grows. And then after the 1, it's going to fall back, as we'll see. But the cosine of 90 degrees? Well, that's the x-coordinate. The x-coordinate is 0, so 0. How about the tangent of 90 degrees, or tangent of pi over 2, since that's 90 degrees? Tangent's the ratio of y over x. 1 over 0, which is undefined. So it's not just the reciprocal functions that can have an undefined one. It's also, sometimes these could be undefined. It's only the tangent. Sine and cosine are always defined. All right, next up, the 180 degrees. So sine of 180 degrees. So we're now looking over here. So the point -1, 0, that's where 180 degrees would be on the unit circle, radius of 1. So sine takes the y-coordinate. The y-coordinate is 0. If you can't get your coordinates right, you're going to mess this up. The cosine of 180 degrees, or the cosine of pi, well, that's the x-coordinate, which is -1. The tangent is the ratio of the two. Y over x, y over x. This is where people make their mistakes. They'll go x over y on accident and get these two swapped, and this one swapped with another one. Y over x, so 0 over -1, which is 0. Finally, 270 degrees, because 360 would have the same answers as the first line. 3 pi over 2 would be 270 degrees. So we're now here at that coordinate. 0, -1. Sine takes the y value, so -1. Cosine of 270 degrees, that takes the x value, which is 0. Tangent of 270 degrees takes the ratio y over x, which is -1 over 0, which is undefined. And again, I'm not going to write the 360s. The sine of 360 is 0, the cosine of 360 is 1, the tangent of 360 is 0, because 0 degrees is coterminal to 360 degrees. That's why when we describe the domains of our angles, like earlier, we go from 0 to 2 pi, but we don't put the or equal in 2 pi. Because 360 is literally the same, anything with trigonometry, as 0 degrees. Ooh, ow, ow. I just bit my fingernail. That's why I'm going ow. So how does an example like this work? Example, I'm just going to say example. What if I asked you what the cosine of 180 degrees is on a test? Now, yes, the answer is staring me in the face right there. Pretend like it's not. Pretend that's not there for a second. Let me make sure if I erase that, it'll go away later. Yes, okay. So I did not write all of those down. I did not just blatantly memorize a unit circle. This is what you do. You draw up your unit circle. You draw the point where 180 degrees would be. You write down its coordinate pair, which at that point would be -1 because you're going left, comma 0. It's always a 1 and a 0, and it's never a 1 and a 1. It's a 1 and a 0 or a 0 and a 1. The 1 might be negative, it might be positive. It depends on whether you went left or down. Negatives for those. Up or right, positives for those. So we say cosine takes on the x-coordinate. The x-coordinate here is a -1. So it's -1. That's the work. That's all you do. If I wanted to do the, let's do the secant of, and now let me erase that. What if I wanted to know the secant of 0 degrees? Well, drop your unit circle. You just put a point where 0 degrees would be on there. Again, that's radius 1, so that point has to be 1, 0. Secant is flipping cosine, excuse me, so that's 1 over cosine of 0 degrees. So the x value here is a 1, so this is 1 over 1, which is 1. That's it. I am about to cough. Hold on. Okay, that's not what I was about to say. I cannot overemphasize how much trigonometry is done on this page. This right here is trigonometry. This is like 75% of the course. Without any of these details, you're going to be missing out on a boatload of problems. You're not going to be able to do anything. If you don't memorize this triangle and you're not just blatantly memorizing a unit circle, which again, not my advice to do, but if it works for you, do it as long as you always get them right. If you're getting them wrong half the time, try something else. Try my method. All you got to do is memorize this triangle, these 4 points on a unit circle, which the points are not memorization. You should understand coordinate pairs. Just know that this is a distance of 1, so these are what the 4 points have to be. Remembering this, and then a smart trig class. That's going to give you a sine or cosine or tangent of literally every single thing on that unit circle. Now, you're going to have to take a minute or two to answer them, but trust me, it's going to make way more sense than just blatantly memorizing things. Why is it that this number is a 1 and this one's a 1 over a square root of 2, which has to be rationalized, and this one's a square root of 3, and this one's got negatives, and this one's got positives? Why? Because that issue of why is going to be a constant threat to your grade if you're just memorizing a unit circle and we're doing a bigger picture problem. This is everything you need as a base to this course, along with, of course, SOHCAHTOA, the reciprocal functions. You know, the Pythagorean theorems will come up here and there. We're not doing it too much for the moment, but they'll peek their heads around that corner sooner than later. In class, every single day, I would draw these two triangles, the 0, 1, 1, 0 points. Sine goes like y, cosine's x, tangent's the ratio, and at least write down ASTC. That right there gets half of trigonometry for me. I don't have to memorize half of trigonometry. I build it from scratch, every single problem. But the scratch building doesn't take long to do. All right, now that I've muddied up that, let's unmuddy it. There we go. All right. Next up, even and odd properties. Clearly zoomed in earlier, or zoomed out. Let's zoom back in. If you are coming from pre-calc 1, which I hope you are, or at least had the equivalent at some point, you studied what it means to be an even or odd function in that course. And in pre-calculus, the usefulness of even and odd functions is in graphing. Even functions, you just draw the right half and you mirror it to get the left half. Odd functions, you draw the right half and then you mirror it left and mirror it down to get the left side of it. The usefulness is not the exact same. We don't use even and odd properties in trig for graphing things. We use it for simplifying things, for pulling negatives from the inside of a trig function to the outside, or maybe just getting rid of the negative completely. But if you go back to the even and odd properties of true functions, not just trig functions, it says basically the same thing without labeling the trig functions. So your even function is cosine. Hold on, I have a distraction. Give me 30 seconds. Sorry about that. I hate having to do that. Cosine and, of course, secant, the reciprocal functions follow the same. This means that the cosine of a negative angle is the same thing as the cosine of the positive angle. That's your only even, or those are your even functions, however you want to say that. And then again, you'll find that your textbook will use the letter t instead. I much prefer just using a theta, or x is just not great, but t, theta, interchangeable. So that's the only even one. It means that the sign inside of it is actually irrelevant. Your odd functions are your sine, and of course, cosecant, and tangent. So of course, cotangent. This means is, scroll down a little bit, the sine of a negative angle is the same thing as the negative sine of the positive angle. Remember, when an angle is negative, that means we're swinging clockwise instead of counterclockwise, which is very atypical for trigonometry. We don't do a lot of clockwise rotations. The only real time we tend to do that is, if you have an answer like 359 degrees, someone might like to just call that -1 because that's a smaller number. And I get that, but it's still not something we do a lot of. There are times when we have to use negative angles for graphing, and we'll get into that, but we're just dipping our toes slowly in. So it means sine of a negative is the same thing as the negative of a sine, or tangent of a negative angle is equal to the negative tangent of the angle. And again, the same definition for the reciprocal functions. So what does this mean? It means a negative inside a cosine can be disregarded, essentially, and a negative in a sine or tangent can be pulled out. So even functions, think about a parabola. The height doesn't matter whether you go left or right. That was an even function. So this is us saying that the output of the trig function would be the same whether you rotate clockwise or counterclockwise. That's kind of like us going left or right in terms of an angle. Whereas with an odd-powered function like x cubed, you had to do that double reflection, and these two negatives kind of act as that double reflection. I don't want to get too heavy into what's going on there. But these can be useful techniques. Maybe I ask you to find the cosine of -45 degrees. Well, you can just say, well, why don't I just find the cosine of 45 degrees? It's the same thing. Or maybe I ask you to find the sine of -45 degrees. And instead of you going, well, let me find the coterminal angle, which would be 315, and then I got to put that 315 in quadrant 1, which gives me a reference angle of 45 degrees, but I got to remember that sine is negative in quadrant 4. Instead of jumping through all these hoops, you can just say, oh, well, the sine of -45 degrees is the negative of sine of 45 degrees. You can avoid creating a reference angle, paying attention to pluses and minuses based on quadrants. So it gives you a shortcut. Are these properties necessary to do anything in this course? Only proofs. Only proofs when we're proving the left side or right side. That's a later chapter. So alternatively, instead of doing these even and odd properties, you can just find coterminal angles and then go back to what we were doing earlier. But this would be a shortcut on that. All right, so we got a couple minutes left. Let's use that time wisely. Let's do this. Example 2. Use even, odd properties to evaluate. Now, because I said to do it that way, you're supposed to. I'm not going to necessarily force your hand to that on a test, but it's still an important thing to try. So sine of -45 degrees. So again, if it didn't say that, what I could do is say, all right, well, this is the sine of 315 because that's the coterminal angle. 315 has a reference angle of 45 because you do 360 minus 45. It feels like you're walking in circles, pun intended. And then you go, okay, well, the sine of 45 involves the 1 squared 2 triangle. You do its opposites and adjacents, but then you go, oh, but we were in quadrant 4 originally, so it's negative. Well, the alternative way of doing this is just saying, all right, sine's odd, so a negative can be pulled out. Just do this. And then you can go, okay, 45 degrees. Well, that's this triangle right here. You can redraw it, 1 square root of 2. So the sine is opposite 1 over hypotenuse square root of 2. This will be negative 1 over square root of 2, which has to be rationalized, giving us an answer of negative square root of 2 over 2 after you finish that up. Again, is it wrong to have done it the way I said but did not write by switching to 315 and all that jazz? No, it's not wrong. I didn't follow instructions, so that's not the best idea for now. But again, trigonometry, we're going to have 10 different ways to do things by the end of this. Maybe a slight exaggeration on 10, but most problems have got more than one way to solve them, and it's about going through all the different ways we could. All right, a couple more. B, the cosine of negative pi over 3. Well, cosine's even, so it means the negative inside can be just completely disregarded. So it's the same as the cosine of pi over 3. So I don't have to switch to 5 pi over 3 and then find its reference angle and blah, 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 blah. The negative just doesn't matter. Essentially, this is because when cosine is based on the x-coordinate, and when you're going right, it doesn't matter whether you went up or down, you went right either way. Sine is kind of the opposite. When you go up or down, it definitely matters whether you went left or right. So that's 60 degrees. That's what pi over 3 is. So we go to our triangle, our 30, 60, 90. Here's the 60 degrees, so this is the angle we're doing. Cosine is adjacent, which is the 1, over the hypotenuse, which is the 2. So the answer is a half. And that's it. No reference angles, no 300 degrees to switch it to, and then back to a reference angle. C, I don't know why I did that in blue. I wasn't paying attention, not that it matters. Cotangent of pi, negative pi over 4. Negative, of course. I don't know why I have the 4 in the negative. I'm trying to beat the clock, so I'm making typos. Cotangent of negative pi over 4. Well, cotangent's reciprocal of tangent, so it has all the same properties. Tangent's odd, which means the negative gets pulled out. So this would be the cotangent, the negative cotangent of pi over 4, which would just be negative 1 over the tangent of pi over 4, if you like using reciprocals. Pi over 4 is 45 degrees. That's the 1 square root of 2 triangle. 1 square root of 2. Tangent of 45, tangent's opposite over adjacent. 1 over 1 is 1. So negative 1 over, this 1 was the 1 over 1 from finding the tangent of 45. But negative 1 divided by 1 is negative 1. Again, didn't have to do any of this. I could have found coterminal angle, which would have been 7 pi over 4, then found its reference angle, which will always be the same as the negative angle. That's kind of a nice coincidence, that's if it's in quadrant 4. I need to specifically mention that. If it was in quadrant 3, that would not be true. So it's usually the same, just drop the sign. So I could have said, all right, the coterminal angle, 7 pi over 4, reference angle, pi over 4, cot of pi over 4 is 1 over tangent of pi over 4, which is 1. But because I was in quadrant 4, tangent's negative in quadrant 4 based on the smart trig class, blah, 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 blah. Same answer.
All right, last 30 minutes for the day. And just pointing out, I know it looks like this just appeared out of nowhere, the thing on periodic functions. It was just a matter of video editing and everything. So I'm just going to give you like 10 seconds before I hit play to start writing that, but it'll be up on the screen for a while I am chit-chatting as usual.
Thanks. Okay, so last little bit of this fourth section. This won't take us too long. I've already established this idea. Periodic functions. These are functions in which, let's say t is the traditional variable of the function instead of an x. We don't like using x as an input variable too often in a trig class, but ironically we will in the next little bit I show you. So t is the variable. P is just some arbitrary number. It might be 3 or 5 or pi or 2 pi or something like that. Usually for us, those last two numbers, because trig. A periodic function is one that just keeps repeating. It keeps repeating, it keeps repeating. It does the same thing over and over and over. So if you were to graph a periodic function, it might look something with better artistic skills. Imagine those all have the same heights. So let's say this is an x value of 1, this is an x value of 2, an x value of 3. The outputs, the heights, are all the same. That's what we're saying here, that some f of t, so maybe this is f of 1, is the same thing as f of 1 plus 1 is the same as f of 2 plus 1. I can just take a number and add 1 and keep getting the same thing over and over and over. Is it always 1? No, it's usually not 1. That's just the context of this example. There's a pattern that loops for eternity, and trig functions are based in being periodic. There we go. All 6 trig functions are periodic. We've established this with the idea of angles being coterminal. So 0 degrees and 360 degrees are essentially the same because they're coterminal. It doesn't matter whether you try and find the cosine of 0 degrees or if you try and find the cosine of 360 degrees. You'll get the same answer because you are in the same position in terms of relative rotation. So more specifically, sine and cosine have a period of 2 pi. Imagine that I just drew the pi symbol there, which means the answers, if the cosine of 0 is the same as the cosine of 2 pi, is the same as the cosine of 4 pi, is the same as the cosine of 6 pi. Now, if you wanted that in degrees, that means they have a period of 360 degrees. But we're not going to be talking about degrees too much in some sections, so I want to get us used to talking radians a little more. So the cosine of 0 is the same as the cosine of 360 degrees, is the same as the cosine of 720 degrees, is the same as the cosine of 1080 degrees, etc., etc. So in other words, I can do it this way. Sine of t plus 2 pi, again, just imagine I wrote the pi symbol there, is the same as just doing the sine of t. And then the same for cosine. So if I ask you for the cosine of 360 degrees, that means you say, nah, I want to do the cosine of 0. Again, same idea as finding coterminal. Periodicity and coterminal angles, same concept. The rest of them have a period, I'm sorry, not the rest of them. I'm just trying to say tangent and cotangent next. In fact, I'm just going to say tangent, since I'm not talking about secant and cosecant. Tangent has a period of pi. Means the tangent of t plus pi is the same thing as the tangent of t. So in other words, if I wanted to do the tangent of 180 degrees, I could just do the tangent of 0 degrees. If I wanted the tangent of 210 degrees, I could just subtract 180 and say, all right, I'm just going to do the tangent of 30 degrees. So this is where things get interesting and lead to some small issues moving forward. Now, reciprocal trig functions have the same behavior. So if sine and cosine have a period of 2 pi, that means cosecant and secant have a period of 2 pi. If tangent has a period of pi, 1 pi, or 180 degrees, that means cotangent has a period of pi or 180 degrees. I want to scroll back up to this right here, and everything can actually be established in this blue ink right here. Look at the pattern of the answers for the sines and cosines. It goes 0, 1, 0, -1. The next thing would be 360 degrees, which is the same as 0 degrees, so it's 0. So it goes 0, 1, 0, -1. The next one would be 0. Then it would go 1, 0, -1, then 0, 1, 0, -1, 0. These four just keep repeating over and over and over. But you have to go completely full circle. You have to go 360 degrees before you actually get a loop, because it goes 0, 1, 0, -1. Kind of looks like an extra negative over here. Let me just clean that up a little. I don't want any confusion because of my poor handwriting. Same with the cosine, 1, 0, -1, 0. There's no full pattern established until you get four of them, a full 360 degrees. So then the next one will be 1, then 0, -1, 0. Again, just keep going in 90-degree intervals. Look at the tangent though. 0, undefined, 0, undefined. Now, it's not the complete picture, but I think it's enough to establish that because there's no ones and -1s, which is what causes us to have to go the full 360 degrees, because 1 and -1 are different, 1 and -1 are different. It just goes 0, undefined, 0, undefined. You actually have that full pattern established halfway in. So you only have to go 180 degrees before you actually see tangents looping and repeating answers. Now, there are times when people accidentally say tangent has a period of 2 pi, and the cool thing is, even saying that incorrectly, you can still establish correct answers, because it's still not wrong that the tangent of 0 is the tangent of 360. It's just that you've gone 2 periods instead of 1. Now, depending on the question being asked, you could get a right answer or a wrong answer. If it's asking you how many periods have gone by, that would give you a wrong answer. But if you're just trying to find the output, if you find the output by using that 360-degree idea, the wrong period, too much, you'll still get the right answer. It's the same thing as like if you try and add a half and a fourth, the LCD is 4, but some students might use a denominator of 8. They can get the right answer. They're just doing extra work to get it. They're doing more work. They're dealing with bigger numbers, things like that. All right, so last couple examples. What are we up to? Example 3. Yes. Example 3. Evaluate by first using the trig functions period to get a smaller angle. So our goal is to, do the sine of 30 degrees or something, but it might start out as the sine of 390 degrees. That's what I'm talking about. So for A, the sine 405 degrees. And for sines and cosines, it's just as simple as finding a smaller coterminal angle. For tangent, instead of subtracting 360, you're subtracting 180. All right, well, sine has a period of 2 pi, which is 360 degrees. So you can take this extra step that some people will do, and they'll say, all right, well, 405 minus 360 is 45. So I can separate this as 45 degrees plus 360 degrees. Some people would just go to the next step and say, all right, now that you have the period added, you can just drop it and say this is the same as the sine of 45 degrees. Again, a lot of people will skip that step and just go straight to here. I don't care what you do as long as you can get it right. Show some amount of work. All right, sine of 45. This is in quadrant 1, so we don't need to do any smart trig class or even or oddness or anything like that. We can just say, oh, okay, well, that's the 1, 1 square root of 2 triangle. I usually don't draw these up to the side, but I will this time. All right, if this is the 1, 1 square root of 2, that was 45 degrees. We knew it was 45 degrees, which means this is the 1, 1 square root of 2. And the sine of that is 1 over square root of 2. But we know that we have to multiply top and bottom by square root of 2 to get appropriate answers that my math lab and your teacher will happily accept, which is square root of 2 over 2. The sine of 45 degrees is exactly the same as the sine of 405 degrees. They are in fact coterminal. It's not always the case with tangents, but it is with sines and cosines. All right, B. The, not sine, tangent of 240 degrees. So tangent has a period of pi, not 2 pi. If this was a sine, you would say that 240 degrees is already fine because that's within 0 to 360. But with tangent, its period is 180 degrees. So you can subtract 240 and 180, which would be 60. So you can say that this is the tangent of 60 plus 180 degrees. So this is the period, any multiple of the period, which means we don't even need it. So this is just the same as the tangent of 60 degrees. Now, I will say that if I didn't tell you to do, if I didn't give you these instructions, if I just said evaluate, I honestly probably wouldn't have done it this way. I would have done, all right, well, 240 is in quadrant 3, tangent's positive in quadrant 3, the reference angle is 60 degrees, and I'd end up doing the exact same calculation. It's just another way to do it. Another student might say, well, this is the same as negative 120 degrees, and tangent is odd, so I can pop the negative out and then do the tangent of 120, which is quadrant 2. Like I said, there's so many different ways to do a single trig problem. All right. Tangent of 60, that equals, let's draw out that triangle again. 60 degrees, which means this is 30 degrees. I know that 3 is a little ugly, but it's there. The number opposite the 30 is the 1, the hypotenuse is the 2, and the square root of 3 is opposite the 60 degrees. You get those wrong, the whole problem's wrong. Get it right. So tangent is opposite over adjacent. The opposite is square root of 3, the adjacent's 1. So this is square root of 3 over 1, which is just square root of 3, no rationalization needed. Finally, C, we are going to do the secant of 1500 degrees. Sorry, distraction. Now, secant is the reciprocal of cosine. Cosine has a period of 2 pi or 360 degrees. There's a bunch of 360 degrees in here though. So you would need to figure out how many 360s there are, and you can just quickly pull up a calculator. I mean, you should be able to do that in pencil paper too, but all right, 1500, I can't see that. There we go, minus 360, that's one of them. Not enough, minus 360. Not enough, minus 360. Not enough, minus 360. Boom, there we go. That was 4 of them, 4 times 360, just so I can write a regular old number, is 1400. So I could draw this up 2 different ways. I can say this is the secant of, it was 60 degrees, right? 60 degrees plus 1440 degrees. Or I could say it's the secant of 60 degrees plus 4 times 360 degrees. That really establishes that it was 4 periods past it, but it's the same answer. Whichever way you do it, you can just say, okay, ignore all the period numbers. This should be the same as the secant of 60 degrees. Again, you can refer to the one triangle you drew up, or you can draw them on the fly. I really suggest, especially while you're learning this stuff, drawing them on the fly to get used to it. Here's 60 degrees, which says same triangle as last time. Square root of 3 goes here, 2 goes here, 1 goes here. Maybe you want to do this. Secant is the reciprocal of cosine, 1 over cosine of 60 degrees. That's an optional way. Or you can just remember, okay, well, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So adjacent over I've circled the wrong thing when I said adjacent. Hypotenuse over adjacent is secant. Hypotenuse over adjacent. So 2 over 1, which is 2. Again, the cosine would be a half, adjacent over hypotenuse. Secant is the opposite order, hypotenuse over adjacent. 2 over 1, which is 2. So I'm a big fan of doing this right here, using the period when you're dealing with larger angles like 1500 degrees and 405 degrees. Do you have to do it with 240? I find a lot of people don't bother, especially with tangents, especially because a lot of people forget that the period's 180 degrees. But you can't forget that, because that's going to be an important fact moving forward in this course. I can guarantee it. you'll be able to still get some problems right accidentally thinking the period's 2 pi, but you will mess up a lot of other things. It's a matter of what exactly we're doing. All right, that is 5.4. So we finished that today, which means it will be due on the 23rd. 5.4 homework due 9/23. Make sure you note that. If I don't have that set up in my math lab already, I will set that up after class. And that'll take us into 5.5. Graphs of sine and cosine functions. Actually, I'm sorry if you just wrote that immediately on your paper if you are taking appropriate notes. I want to do a problem that I meant to do a couple sections ago, a word problem. So quick, just a quick word problem, 5.2 or 5.3. I can't remember which it was off the top of my head. Sorry for that, but either way, it's important. A guy wire runs from the ground to a cell tower. Wire is attached to the cell tower 150 feet above the ground. The angle formed between the wire and the ground and the wire is 50 degrees. Questions are, how long is the guy wire? And how far the base of the tower is the wire anchored to the ground? Let's do it this way then. I don't want it to look like that. How far from the base of the tower is the wire anchored? I'm going to draw up a picture for this. You know what they say, a picture's worth 1,000 words. Now, I don't have to give you a picture for this. You can establish it from all of this. So let's say that's what we're doing, because that's really what I'm doing. A guy wire runs from the ground to a cell tower. So we're going to have a cell tower somewhere, and a wire is going to be running to the top of the wire. And it doesn't say that I'm taking this word for word, but I kind of feel like it should. But you usually don't run wires along the ground, right? It's usually from something to the top of something. So let's say right here is our tower. This is our tower. And we've got a wire attached to the top of it. And it's running to the ground. Now, this wire that's attached, 150 feet above the ground, so it's a 150 feet tall tower. It's attached somewhere over here or over here. Let's attach it on the left. So here is the anchor point. So this is your ground. Here's your wire, as straight as I possibly can without taking 10 minutes blindly doing it with a ruler. Imagine doing something blindly with a ruler. That sounds fun, because that's the situation I'm in. So this is the wire, not the wonderful TV show from the early 2000s, the actual literal wire. And then again, our ground is down here, obviously. They want to know how long is the guy wire, so they want to know the length of this distance. And they want to know how far from the base of the tower is the anchor point. So this is our ground, and we need to know that distance. So if you wanted to give these letters, the hypotenuse is the wire, so I would call that our C. And the 150 you could call the A or the B. I'll call it the A, which means this distance would be the B. And they told us that the angle formed between the ground and the wire is 50 degrees. So this right here, this angle between the wire and the ground is 50 degrees. This is, of course, a right angle because this is not the Leaning Tower of Pisa. It's built straight up, appropriately, good construction. This is what trigonometry is all about. It's what it's for. It's for word problems. Why is that happening? Let's go right there. We go. Word problems. Life is a word problem. Engineers do this kind of stuff all the time. They know they got a 150-foot tall tower. They have a little electronic device that they can measure. They can walk some distance. It doesn't matter how far they walk. They could have walked to here. They could have walked to here. They could walk way out over here. But then they face the tower and they go beep, boop, beep, and it says there's a 50-degree angle. Pretty easy. Or you could get old school and get yourself a protractor and put it at eye height. You would have to then subtract the height from your eye to the ground in that case. It's small and almost negligible. You'd get a close answer if you didn't, but it wouldn't be accurate. In engineering, it needs to be accurate. What is the point of this problem? How do we use trig to do this? Our goal is to find lengths B and C. How long is the guy wire? So that is answer C. I know it's question A, but that means we want to find out the distance C. How far from the base of the tower is the wire anchored? That's that distance right there, B. So those are the goals. What we want to do is we want to use a trig function that picks out the known value and also the one we need. We want to use a trig function that picks out the known value and also the one we need. And what am I referring to? Opposites, adjacents, and hypotenuses, hypotenuse. So in terms of 50 degrees, this 150 would be the opposite. The length of B would be the adjacent, and the C would, of course, be the hypotenuse. The 150 is the known value, so we have got to use trig functions that use the opposite. We need to use trig functions, and because there's more than one choice, I'm only going to show the work for one, but there's more than one choice. So we've got to use a trig function that uses an opposite. Now, how do we know? Because sine uses opposite, tangent uses opposite, cosecant uses opposite, cotangent uses opposite. Which of those four should we use to do A? How long is the guy wire? So we know we've got to use a trig function with opposite. C is the length of the wire, which is the hypotenuse. So we need the trig function that uses opposite and hypotenuse, which means we have two choices. We could do sine or we could do cosecant. I can imagine that you guess which one I'm going to go with, sine. Cosecant does the job, but it's a bigger pain in the butt because we're used to sines, cosines, and tangents. You might not be yet, but you will be moving forward, I hope. So for A, we're going to write the sine of 50 degrees is equal to, now sine is the opposite over hypotenuse. The opposite is that known value of 150 feet over the hypotenuse is that blue distance C. I didn't have to be blue. I'm just trying to emphasize, since I called it parts A and B with uppercase letters. Guess what you do from here? You just solve for the unknown variable. Now you might say, I've never solved a trig function. This is completely different, and you're wrong. It's the exact same thing you've done in algebra. Add, subtract, multiply, divide things on both sides to get the variable isolated and all the numbers on the other side. That was a redundant statement, but it's still important to say. Now, the variables in a denominator, how do we get rid of variables in denominators? We're going to multiply both sides by that variable. So I'm just going to rewrite it. The sine of 50 degrees is equal to 150 over C. We need to multiply both sides by C. Why do we do that? Because tops and bottoms of fractions will cancel each other out. I'm going to undo me writing the canceling, but you'll leave it in your notes probably, which is fine. Again, those C's on the right-hand side cancel. So we get C times the sine of 50 degrees. Now, you might want to put the C after it, but you might get confused and think the C is part of the angle. So I actually really prefer it this way. Wrong color. C times the sine of 50 degrees is equal to 150. And we're trying to solve for C, so we divide both sides by the number it's multiplying. Sine of 50 degrees is just a number. We don't know what it is. I'm not asking for it. We're just going to divide both sides by whatever that number is. You're going to do this 1,000 times by the end of the semester. Why do we do that? Because then these cancel, giving us just a C on the left side. C equals 150 divided by the sine of 50 degrees. Now, depending on the formats of tests, if this was a classic, in class, in person, I would say this is the answer. But usually with applications, they want decimal values. So what we would do is round to the nearest tenth. And I forgot to write that in the instructions, didn't I? I did. Round to the nearest tenth. It's an application. While yes, analytically, 150 divided by sine of 50 degrees is an accurate answer. If it's an application, we want numbers. We want numbers our boss can understand. So we go to our calculator, we turn it on, we clear our screen. What's the first thing we always do with trig with a calculator? We check our mode. I'm in radians, which is bad. I need to switch it to degrees. Hit enter. Hit second mode, which is quit, to get out of that. And then I can type 150 divided by the sine of 50 degrees. See, if I had used cosecant, my calculator wasn't going to be able to do that. I'd have to do a reciprocal on the own problem. Don't use cosecant. And you get 195.8 when you round appropriately. 0.8 feet. So that's the length of the wire. For part B, we wanted to know how far away was the anchor point. Now, the point of this problem is really in the real world, you wouldn't have attached the wire yet necessarily. I said necessarily, might not have. You may want to know how much wire you need first, cut it, then do the attaching. So doing the trig first would be important in that regard. Alternatively, you just throw the wire up there and cut eventually. And if you don't have a way of measuring it, you'll be able to measure it in post using trig. Okay. Next question was, again, how far away from the base of the tower is the wire anchored? So the base, that's the horizontal distance between anchor point and the bottom of the tower. We call it little b, which is the adjacent in terms of 50 degrees. So again, we want to use a trig function that picks out the known value and the one we need. Now we actually know two values, technically speaking. We now know the hypotenuse and we know the opposite. So you could say, I'm going to use the hypotenuse and the adjacent, and I'll go with a cosine. I'm going to suggest that you don't, though, and here's why. This hypotenuse, we round it. When you take rounded answers and put them in trig functions and then round again, you get something known as error truncation, and the numbers over time get worse and worse and worse. If you keep taking a rounded number and putting it in and getting something, rounding that, putting it in, getting something, rounding that, putting it in, getting something. After you do that, maybe 4 times, maybe 10 times, maybe 100 times, your answers start to turn into trash. How quickly they turn into trash depends on what mathematical function you're doing. There's a massive field of mathematics that just studies error truncation. It's pretty confusing at first, but it's pretty cool afterwards because it does a lot of useful things. What's the point of this conversation? Don't use rounded numbers to find something else. So try and avoid that if you can. If you can't, then use it. But if the answer is supposed to be, maybe 120.1, you might get 120.2 using a rounded value first, and it'll be wrong in my math lab. And a homework problem that's going to frustrate you being so close. You might not even go back and do it again. On a test, you'll be really frustrated, and then you'll have to email me and say, hey, check my work. If you didn't do any work, I wouldn't be able to give you credit even with a rounded answer like that. No work, no partial credit. So I'm going to suggest don't do the hypotenuse. Use the opposite because it was a perfect number, 150. We need the adjacent. What trig function uses opposite and adjacent? Tangent and cotangent. What's the simpler one? Tangent. So we'll say the tangent of 50 degrees is equal to its opposite of 150 over its adjacent of what we called b. I'm using the coloring just to help a little there. So we're trying to solve for the b. 150 degrees, no, not degrees. Why did I write degrees there? 150 over b. So we multiply both sides by b to get it out of the denominator. Your variable is not always the denominator in these types of problems. It could have been the top number, in which case multiplying both sides by that bottom number, you'd actually be done. I'm giving you the most complicated ones so that you can do the simpler ones without me giving you an example. So b times tangent of 50 degrees is equal to 150. But we're trying to solve for b, so we divide both sides by the tangent of 50 degrees. That's just a number. I'm not showing you what it is, but it's just a number. So b equals, after the canceling, 150 divided by the tangent of 50 degrees. Look at how close these answers are in their actual form, in the exact answers. When it's written in this version, it's exact. When we round, it's approximate. So it's calculator. The mode hasn't changed. 150 divided by tangent of 50 degrees. You can check the mode if you really want to. Mode, yep, we're good. So 125.86, which would round to 125.9. Be careful with your rounding. And that's in feet. So that's the horizontal distance. There we go.
All right, so that'll be it for the day, ending just in time. Just reminding you what the due dates for homework assignments due today, 5.1 and 5.2, and then 5.3 and 5.4 are due in a week since we finished both of those sections today. And like I said, I gave you that the word problem at the end. I said I was going to do it earlier. I had things out of order in my head when I started this class because I was coming right off of my 154. Like I said, I literally have no time to breathe between classes. So occasionally I might say something silly in the intro like that. Again, that was just out of place. But hopefully everything was understood today. You were a little quiet. I didn't get too many questions in PMs. But remember, you can always ask me questions in chat. I'm always here while class is running. And then after class, feel free to email me if you have any questions. Good luck with the homework. Again, email me if you have any questions. Take care, have a good weekend, and we'll see you on Tuesday.